Good evening, everyone. Can someone confirm if my screen is visible?
Yes.
Okay, thank you. So, welcome to week 9 discussion section. Um, yeah, so before we move on to this, do we have any doubts for week 8 questions? How was that for both of you?
I got 80 marks.
Okay. So, 80 out of what? Unless I know that, I won't be able to understand.
Ma'am, but that the problem is not resolved, that exam. Na?
Okay. Did you get a chance to mail them?
Ma'am, I have mailed, but there is no reply. It is now 1 week.
Okay. I mean, because in this case, even I cannot help. Like,
No, no, at least my mail, they will not respond. At least your mail, they will respond, whether they will include or not.
uh, okay, then you can mail them, keep me in CC. Let's see what happens. I'll try to respond on that. Is that okay?
Yes, ma'am. But I don't have
Oh,
your mails. So will you please share your mail?
I just shared in the chat window.
Okay, ma'am.
All right. Okay, let's go back to the assignment questions then. So, do you have any doubts in week 8 assignments? Any of you? Okay, if there is no question,
And question number 5 is question number 5.
okay, you have one question. Let's go there. Week 8. Question number 5. This one?
Yes, ma'am.
Okay, what was the answer?
Can't say, ma'am. C option
Can't
is the
say.
The answer
Okay,
is
and
C. C is the answer, ma'am. I marked D. So C is the answer.
yeah, that's why I'd asked to be careful because these two seem like similar things, but I think over here you had to kind of gauge the range of values that A will be taking, and based on that, you could have just said some kind of comments like whatever the value of A is, depending on that, you don't know what the answer is going to be. I think you could have said, can't say. I mean, this answer I cannot resolve based on these two. It's like one or the other. So, what answer did you mark, Padmavati?
ma'am. I have also chosen the option D, ma'am.
Okay. What about Shivank?
Initially, I marked, I changed it to D and I regret it.
Okay, so all of you have done that. Yeah, I mean, this question was like that. It is like, I mean, these two options should not be given in the same question. It is
Actually,
a
the
bit difficult,
example
but
was taken from a famous book, and I saw that, and
mm-hmm.
but but the question wasn't very similar. But yeah,
Right, right. Yeah. I mean, either of the cases, but I still feel like questions, if you are sitting, you should, um, it's fine, whatever it is. So let's see that we don't do such things in final exam. Um,
yeah.
Also, I think once they release the solution to these questions, you'll be able to understand much better as to where exactly there would be a very minor mistake or minor difference in understanding, and then we would have marked sorry, D instead of C. Okay.
Question
Any
number
other
10.
question apart from
Question
this?
10.
Question 10. Let's go there. Yeah. So in this, which option is the confusing one?
I mark C,
Exponential.
but answer is D.
Answer is D. Okay, let's see. Uh, just a second. I'll also check the assignment website. Okay, let's see. So the first one is the answer is D, is it? True and true, false and true. Okay. If a system is asymptotically stable, then it will definitely be an exponentially stable system. The second one is the barrier certificate approaches towards infinity as the system state approaches towards the unsafe region. This is fine because if you want to go to the safe region, this has to go towards either negative or zero. Let me just check. Yeah, this was the barrier function, right? So here, as long, I mean, the more you go towards a larger value, you are going to get an go towards the unsafe region. This is about the barrier function option, okay? And then if your barrier function is less than equal to zero, uh, then you are in the safe region. So this is your safe region. Yeah, so this option is definitely true. So out of these two, you had to pick. Now let's see about the first one. If a system is asymptotically stable, then it will definitely be an exponentially stable system. Okay, where is asymptotic stability over here? Mhm. Okay, so the condition for asymptotic stable is that all the eigenvalues of this has to be less than 0. Of A has to be less than 0, right? Which means that this has to be less than 0. So this is asymptotically stable. So let's write down that point over here. All eigenvalues for A is less than 0. All right. Now, if we actually go to exponential stability,
It is on the page 9, ma'am. Yeah, here it is, exponential stability.
oh yeah, right. So here it says that if the system is stable and there exist two positive constants C and I such that x of t naught is less than delta implies this thing. Notice that it implies asymptotic stability, that is this. So this statement actually says that exponential implies asymptotic, right? So the option over here, it's actually mentioning that exponential implies asymptotic, right? Let me just clear up the space. Okay. Um, yeah. But over here, this statement says that asymptotic, if it is asymptotic, then it will definitely be exponential. So this implies this. So this is the difference. This one is the true thing, and this one is the false statement, right? This is what we got from the slides. Is this clear? It just had to be opposite and
Yes.
it would have been a true statement. Okay. Other questions? Okay, so should I move on to week 9 questions?
Yes.
Okay. Yeah, so in week 9, most of the questions were on this LQR controller. Okay, so let's see what those questions are. So the first question, are you able to like read the text?
Yes.
Yeah, ma'am.
Okay, all right. So here the question says that choose the correct property of the weight matrices that are used in LQR loss function. So in general, there are some properties of this loss function weight matrices. Okay, so this is a very straightforward, but I'll still try to give you some hints. Let's first go to this LQR itself so that yes. So this is your loss function, right? If I'm not wrong. And there is this Q1C, which is your weighing matrix. Okay, so this is how it is represented: X transpose Q of X, this whole into dt, and then you integrate it over your interval, whatever you have, right? Or I mean the quantities that needs to be there. So since this kind of a computation needs to be done, Q needs to have some specific kind of properties. Only if that is possible, then this kind of a computation is possible. Okay, so you would find the answer over here, and the only reason to have that those kind of properties is to make these kind of computations possible. And your loss function, since yeah, I mean it just goes with the definition of your loss function, so I would just still, oh, okay, um yeah, just put the slide number so that you can refer that. Okay, let's go to the next question. Yeah, so over here we are going to use your loss function. Okay, so the objective of your LQR is to design an optimal control signal that minimizes the following loss function. So this is your loss function right now. All right. For solving the optimization using dynamic programming, we introduce the following notation. All right. Here, Vk is the minimum loss from k to nth iteration. Then state whether the following is true or false. Min of j is equal to V naught. Okay. So over here, again, this is a very theoretical question, but let's just break it down into some components. So here, what are we talking about? We are talking about the window of n iterations. Okay. So if you start from k and you go to the nth iteration, okay, so the question says that is vk the minimum loss over here? That is the question. Okay, and how do you get your vk? Your vk is identified by this equation, that is minimum of over all of these, like you put the values over here, I is equal to k to n minus 1, right? And this x transpose q and x, this is the same kind of format that we put over here, x transpose q and x, right? So this is x transpose q1 x. Then yeah, this q, sorry, u transpose q and u, and then we have two times that in the next. So this is a little different, but it is because of this equation what we have over here, right? So yeah, and again over here, what do we try to do? So we try to minimize this, that is definitely there, that is your loss function. I'm just trying to see. Yeah, so from 0 to this is done, this is fine. So yeah, so this equation says that from where is your thing starting? It is starting from k and it goes until n minus 1, right? So your vk is minimum of u of k up till u of n minus 1. Your u is the input, right? And then you sum it over I is equal to k to n minus 1, right? And then all this thing is there. Now over here, when you actually see, for any given x0, the problem is defined to determine the control sequence. This is your control sequence such that your loss function is minimized. So here the loss function was talking about 0 to n. But what are we talking about over here? We are talking about k to n, right? So the equations that are given are actually given from k to n minus 1, right? So you have to just see if it is matching, and since your min of j is equal to v naught, that is the question or not. So you have to just see if so basically you are defining your, this is your minimum of j, that is your this loss function. Okay, so you can just check that part if it is resembling, and if the minimum of that is we are setting it as v of 0 over here. All right, so I think this should also be okay, but let me know if this is complicated or something is the problem. Is this okay?
So why, ma'am, we have not taken k from 0? Why we have started from k to n?
Sorry, why are we not taking?
From k is k, we have started from k, not from 0. But definition says we have to take from 0, 0th iteration.
Where does the definition say? Definition also says from the k to nth iteration. So vk is from
Slides, in
k
the
to
slide, it
nth.
is in the slide it is written that we have to control sequences from 0 to u0 to un minus 1.
Okay, yeah, that is there. I that's why I was asking you to resemble both of them, right? So this is one system, that is another system. Okay, if you have that thing, let's see. So over here I have written vk, right? And we have one thing called v0 over here, right? So for your vk, what are the control signals? For your v0, what are the control signals you were getting? u0 to un minus 1, right? U of 0, U of n, up till U of n minus 1, right? Which is given in the slides. Now V of k over here, what all are you getting? U of k plus 1, up till what? U of n minus 1, right? Because over here we have n of this, and k can be anything. K can be your 0 also. So if your k is 0, does this thing still fit in this equation? That's the question.
Okay, okay.
Okay, so it's a very, very simple question. I think it should be okay. And over here also, what do you get? So this is the control sequence when your loss function is minimized, right? So over here also, this is going to be your control sequence at what point? When your loss function is minimized, right? So do you see the resemblance now?
Yes.
Okay, great. Okay, so should we move to the third question?
Yes.
All right. Okay, so third question says a first order continuous system is represented by the following differential equation. This is your differential equation. X dot of t is equal to x of t plus u of t. We want to design a feedback controller such that u of t is equal to minus k square x of t. And desired equilibrium condition is this: x of t is equal to 0 as t tends to infinity. Okay, what should be the value of k for the above system to be stable, right? So you have to get the value of k. So let's start. So your x is given as that. So if you substitute u of t in this equation, you get x of t minus k square of x of t. Oops, right? And that is what? 1 minus k square x of t, right? So now what am I doing? And what is this? This is dx by dt is equal to 1 minus k square x of t. So if you do dxt by x of t is equal to 1 minus x square d of t, right? You integrate both the sides, all right? Then you will get some equation for x of t. Okay, you will get something. You'll be able to solve this, right? Or should I solve one more step? Or maybe just help me out right now. Okay, so this is from 0 to t and this is also from 0 to t only. So what is the integration of this kind of an equation? 1 by x dx. What is the integration?
Log x, natural log x t.
Log x. Correct. Yeah. So we have this t of 0 and then you have 1 minus k square t. So you will substitute your values, right? And eventually you will get your x of t. I think now you should be able to get. So whatever you get over here, based on that, what do you have to calculate? You have to calculate that at what point, no, that your since your x of t is going to be 0, if your t tends to infinity, what is the value of k over there? Okay, so I think you will be able to get it, but yeah, the equation will be in some kind of exponential form because you have a log over here. And yeah, Hmm. Just make sure that whatever is in your exponent part, right? That thing, that thing should be greater than zero, I guess. Yeah, it should be greater than zero. Okay.
So, ma'am, whatever will be in the exponent part, we have to put the condition that it should be greater than zero. Just that.
I think yes.
Okay.
Yeah.
Why greater than 0? I think if you take e to the power 1 minus x square, it will come. Xt is equal to
Hmm.
1 minus e to the power 1 minus k square, and then exponential should be in the fraction, so that
No, your exponent. No, not the. I mean, the entire part that is there, that should be greater than zero, right? Only then, when your t tends to infinity, your x will be zero. Otherwise, if your t tends to infinity, your x will be minus something. Oh yeah, it should actually be less than zero. You're right. Yeah. Okay. So try to make exponent part less than zero. Yeah, you were right.
Ma'am, why we are taking less than zero? I still don't get.
Because we have to satisfy this equation for your x of
Okay.
t.
Okay. Yeah, yeah.
Yeah.
Now I got it. Yeah, yeah. Now.
Yeah.
Okay.
Okay, so shall we move to the next question?
hello, ma'am.
Yes.
Next question.
Okay. Yeah. So the next question is a follow-up question of the previous one. It says consider the same system and stability criteria given in question 3. Okay, so we have to consider the same equations. The performance of the system is measured by the following loss function. This is your loss function. Now, given your m is greater than 1, we have to compute k such that j is minimum. So we actually have to find out the value of k for which dj by dk is equal to 0. Let's see how to solve this now. So actually it starts from the point this equation stops. Okay, but let me just write down a few things over here. You have your x of t is equal to x of t plus u of t, right? That's what we have. And what is our u of t? That is minus k square x of t. Okay, and we got x of t is equal to something, right? Based on x0 something 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 that we got over here, right? So now what we have to do is in that thing, because you will be having yeah, you will be having M. Do you have M? No, you just have K over there, right? Let me try not to mix, and you will still use the same equations, but I'm just writing what is required for this question over here. You have your J, which is 0 to infinity, x square of t plus m of u square of t and dt. Okay. From your other question, you are getting x of t is equal to x of 0, something, 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 right? This is from question 3. So try to get the answer right in question 3, only then you'll be able to get the right answer in question 4. All right. Now, once you substitute this value of x in this, okay, and for u, what do you have to substitute? You have to substitute minus k square of x of t. Okay. So again, x of t is this part. Over here also, this will be substituted. So at both the places, you will get substitutions, and then you will get some equation of j is equal to this big equation. All right. Now, after that, you would need to do an integration, because this is integration. I mean, the integration should be solvable. Okay. And once you have your j, actually first you will get j is equal to integration of 0 to infinity of that equation that you get after substituting this x square by this formula, and u square by this first, and then xt with this. Okay, then you will get, then you integrate it, and after that what do you have to get? You have to get d of j by d of k. So once you do that, you will be able to get some value of k. Okay, so you will be getting some equation over here. All right, and since your m is greater than 1, you will have to shortlist whatever options you have. But your, depending on the value of k that you get from the question 3, you will have to choose if there will be two options actually. Okay, so it will come in, let's say it came in this plus minus format, let's say I'm saying. So you will have to see if, depending on the k value, which is from the previous equation, and the m value, which one of that, like, will only the plus sign fit, or will only the minus sign fit, or will both of them fit. So you'll have to check accordingly. Okay, based on the value of k that you get from the equation. Is this fine?
Yes, ma'am.
Okay, so let's see this question. Oh, this is also similar. It says a first order continuous equation is represented by the same equation. Okay, now we want to design a feedback controller such that u of t is equal to minus p of xt, and the desired equilibrium is this. So if your ut over here is what? Minus k square of xt. In the previous question, you had x dot of t. This was the same. In question 3, u of t was minus k square x of t. In question 5, you have u of t minus p of x of t. So what can you, let's say if everything is same, what can you derive from here? You can say that your p is equal to root of k, if I just write it like that, or maybe plus minus. No, 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 it's opposite. K square is equal to P. So you can say that your K is equal to plus minus P. Now, what else? So x of t is equal to 0, t is tends to infinity, again the same stuff. Now the performance of the system is measured by the following loss function. So over here also they have given a loss function, which is this j is equal to x square of t plus 5u square of t dt, 0 to infinity. And you have to compute p such that your j is minimum, which means we have to do dj by dp is equal to 0, right? This is what is given. So what is the previous question? X square t plus mu square t of dt. So this is question 5 equation. Question 4 equation says j is equal to x square t x square t plus, what is it, mu square t u square t dt. Okay, so here you can say that your m is equal to 5, right? So depending on the equation that you got from here for the value of k, okay, you will have to do some kind of substitution over here. But let me see what changes. So your k is being computed for the previous equation only, right? Hmm. Maybe you will have to do this all over again by taking p as the new um, coefficient of x of t. Mm. Can we simplify it more? Or if I just write x square of t plus u square is what? M p square x square of t dt. Hmm. I think I would suggest you to solve it. Solving would be better than checking the values from the other questions. Maybe solve it and still go ahead and check with the other questions to see if they at least match these kind of things. Okay, these are the things that is going to happen, but I don't want you to like complicate stuff. You can just solve this question altogether. Okay, so your m is also 5 over here. So 5 of u square t, and your u is given as pxt, which is going to be p square x square of t. So you actually have to solve this first, j, get the equation of j, and then you do dj by dp is equal to 0 and get the value of p. Yes, tell me. You were saying something?
Ma'am, hello. Am I audible, ma'am?
Yes, you are audible.
Yeah. So, ma'am, from previous question, we just have to substitute p square is equal, k square is equal to p and m is equal to 5 from the previous option, whatever option we get.
See, I think you can still do that. Okay, but I would ask you to first solve it because I haven't solved exactly like the full part. But this resemblance you can always get. But I would still say that you solve this question, okay? And then based on what you get, you just cross verify if this is happening or not. If these conditions are happening, then your question 3, 4, 5 are right. Okay, that's the best way to test out if your question, if your solving is correct or not. Okay.
Yeah, and ma'am, the equation that we are getting xt is equal to x0 plus something, for example. So x0
Mhm.
should be redundant, na?
X0 should be what over here?
Yeah, x0 should be redundant, I mean, or it is used
It will be
in.
redundant, right? It will come out. You will have to take some common out of it. And x0, make sure that since it is a constant, it comes out of the integration. It's not used in the integration. Okay.
Yeah, sure.
Huh. And you will be integrating it on t, if I'm not wrong, right?
Yeah, yeah, yeah.
So anyways, your x is not a variable. Okay, so solve question 5 independently, and then whatever values you are getting, whatever equations you are getting, cross check your question 3 and 4 using this. Okay, that is the advice I would give you. Is that fine?
Yes.
Okay. So next question is choose the correct option to fill in the blanks in the following definition. Flow function of a dynamical system is globally Lipschitz. Continuous implies this less than, okay, for a real constant k greater than 0 in domain D. K greater than 0 and your domain is D. So this is less than what? This is again a very theoretical question. I would just point you to the slides. Let me see. Lipschitz. Mm. Here we came on control barrier functions. Lipschitz property is not given, is it? Yeah, this globally Lipschitz globally is fine. Sorry, it will be here only somewhere. So I don't know if it's here or not, but try to check the definition for Lipschitz continuity. Okay, and this is like that, so I'm not giving the answer. But if you check the definition of this, you should be able to get the exact same equation. Okay. Okay. Let's go to the next one. For designing a CLF CBF based optimal control strategy for safe and performance aware control that outputs the optimal control action U for a dynamical system x dot is equal to fx plus gxu with cost function this. Let me just write all these things down. f of x is plus g of xu. This is your control action. Your cost function is u transpose plus p delta square. Your h is positive definite. This is similar to your first question. Symmetric. And this is a positive slack. Okay. So you have to check that what is the role of the slack variable delta. All right. Let's see. This question over here is from this part. Yeah. You have to do combine CLF and CBF for optimal control, right? So which slide? 31. So this is the same equation. You have CLF formulation of quadratic cost function. You have this cost function UHU transpose that we have. Okay. And then you have the safe and performance aware control input. This is your control input. And you have these constraints. So there are two constraints in your CLF and CBF. One is that is putting some kind of constraint on your CBF function, which is this equation. The other equation is this, which is trying to put some constraint on your CLF part. Okay, so over here, you see that where your slack is being used and what is being actually used for. Okay, so there is no relaxation for CBF, but only for CLF. Um, so yeah, see that which one is enforcing what and which one is actually using your constraint. So the question says, what is the role of your slack variable? So check where your slack variable is being used and why is it being used. Okay, so I think you should be able to find the answer. Yeah, slide 31. I hope this is okay. Should we go to question 8?
Yeah, ma'am. This is fine.
Okay. All right. So other question is again a very theoretical one. But let's see. In a safe control strategy, the CBF Bx is chosen such that B dot x is less than lambda B of x. Lambda is greater than 0. So your differentiation has to be less than, is actually has to be a negative number probably. If your B is negative, B is positive. Which of the following best describes the behavior of Bx and the system when B of x is greater than 0 and B dot of x is less than 0? Okay, so you will have to analyze if your Bx is greater than 0, then what happens? And if your B dot x is less than, this is B dot x, right? Yeah. Then what happens? So maybe for this part, you can refer this slide. Where is it? Yeah, from 30 itself, you should be able to get something. Okay, so just make sure that lambda greater than 0 is already given to you. And maybe over here you can also try and check this part. Maybe from the previous lecture, there was this barrier function part. Yes, this diagram. Okay, so try to check this, that if your B of x is less than 0 and your lambda is greater than 0, then what happens, and all those kind of things. So maybe refer slide 36, 37 also of week 8. This will also help you in some kind of analysis. Okay, so just make sure that your bx is greater than 0. It is already given, so that is the case for this one. So if your bx is greater than 0, it is over here. But because your lambda is greater than 0, then what is the kind of thing that is happening? What more? Yeah. I mean, this is also given greater than 0, and this is greater than 0. So basically, your b dot of x is less than 0 only. So you just have to check for that condition, that if your rate of change of bx is less than 0, then what happens? Okay, should we move to question 9?
Yeah, ma'am, please.
Okay, sure. So next question says match the following: safe control, asymptotically stable, exponentially stable. Okay, again, these are theoretical questions, but let me see. So one thing I would just tell you that since your control barrier functions, they are used for safe control, so you can use that option for this. Okay, that is like straightforward. But you can check for these B and C because they both are for CLF, right? So try to check what is the answer for those two. And again, over here, try to see asymptotically stable and exponentially stable. You should also try to refer this week and the last week also, because I think some of the concepts from there can be carried over to this. Okay. Next question. Find out whether the following statements are true or false. All sub-level sets of CLF are invariant. 0 of CBF is invariant. And 0 level set of CBF is safety boundary of the system. Again, theoretical questions. I'll just maybe put the slide numbers. Sub-level sets, right? Actually, here also you can refer. So slide 28 for the previous question. These are LQR, so is it not given in the slides? Hmm. So maybe you can go through this one. I don't know if the thing is given or not, but sub-level sets are actually those for, yeah, these are your regions in the state space where the system exhibits stable behavior. Okay, so yeah, maybe try to check what is the sub-level set for CLF, what is it for CBF, and what is the zero level set also. So you can check S of 0. So any alpha is given as this, V of x is less than equal to alpha. So this is similar to that. So if you're over here, I have put alpha. If this is a generic equation, if you want to just check for all sub-level sets. Okay, but if you want to check for specifically zero sub-level, what you will have to do is you will have to do alpha is equal to 0, and then eventually you will have to check like that. But for CBF, this is for CLF that I have written. CBF, the equation may be different. um, yeah, so you can check that part. But why is it not given over here anywhere in the slides?
In the CLF definition, they have mentioned the about sublevel sets. If you just, yeah, so
CLF,
there it is,
oh
uh,
yeah, it is given,
with
right?
bounded
Sub-level.
sublevel sets. Yeah.
Yeah, yeah, right,
What?
it is given.
Yeah, yeah. So if you can please explain, ma'am, that.
You want me to explain these sub-level sets?
Yeah, yeah, just that part. And what about zero? Any condition, any expression that can help us to.
Yeah, so this is what I have explained for CLF. Okay,
Yeah, yeah,
so this
yeah,
is
yeah.
what will be for your CLF. So even over here, right? But since it is for CBF, the zero one, I'll just let you know. So here you will just have to check if these are invariant or not. Okay, that is the first part. Now in the second one, this is for CBF. So let's see the equation for that one. Hmm. Okay, so what happens in the barrier functions? Again, it is similar, but the only thing that changes that your barrier function is less than equal to alpha. And since your alpha is equal to 0 over here, you will have to check that if your S0 is first of all invariant or not, right? You will have to check for B of x is less than equal to 0, or you have to check that if that thing is the safety boundary of the system. Okay, so this S of 0 is B of x less than equal to 0, right? You have to identify, is this your boundary of safety? All right. I think your boundary was bx is equal to 0, right? If I'm not wrong. Based on that, this diagram, this is your bx is equal to 0,
Hmm.
right? Inside it is less than and outside it is greater than.
Outside is greater than.
Hmm. ठीक है. I think you should be able to get some answer based on that. Does this help, this explanation for both CLF and CBF?
Yeah. It helps. Actually, it
Ma'am,
was given at the bottom,
I'm sorry.
the definitions. The definitions were mentioned, but the asterisk mark was there, and it is mentioned at the bottom. So I forgot to saw it. So see, you can
That's
see
okay.
here they have. Yeah. Okay.
Mm, you mean over here, right? Oh
Yeah,
yeah, it is
at the
given.
bottom.
Right,
At of
yeah.
yeah.
Set of is such
That's
that
what I
Vx
was.
is less than C.
Yeah,
Yeah,
yeah, yeah,
it is.
yeah, yeah.
Okay, I guess this is it. Let me know if you need any more detail on any other questions. I'll wait for a couple of minutes.
ma'am, can you explain the significance of CELF and CBF? Though
Okay,
the
these are
definitions.
two different functions actually. One is a function for stability and the other one is for safety. So your CLF is actually mm, okay, this is also for safety only. Let's see. I thought this is for stability. The above strategy, it ensures the safety invariance. All right. V is your around the equilibrium point. This ensures exponential stability with gamma decay rate. Okay. Let me check CBF also. So this is also if there exists a gamma such that your controlled is this. Hmm. I think control barrier function is actually depending on your that boundary. So both of them try to get some kind of function that tries to be stable and it tries to ensure some kind of safety also. Okay, but barrier function does that with this boundary coming from this picture. It has a boundary, that barrier function. I think nowadays control barrier function has actually picked up pace and it is being used a lot in the research community for safe autonomy or any kind of, safety critical devices, those kind of things.
So it is written that CBF is for safety and that CLF is for the performance.
No, CLF is also for safety only. Both of them, I think they are for. Uh, so even if they say performance here, right?
Here
What
it is
is your?
written,
Yeah,
the
yeah, that is
combined.
written over there. Mm, yeah, I guess this one does not take safety into account, right? CLF does not do that. Yeah, right. It is stability. So over here, this one is like optimal. So this is combining both of them. CBF is being used for your safety. That is there. This one is being used for performance, and by performance, they mean stability. Okay, so the first statement that I made was actually right. That one is for stability, the other one is for safety. Okay, and if somebody wants to use both of them in some kind of system, they do this hybrid approach, and they get both of the, like, safety aware and performance aware input as well.
Ma'am, just check the mail. I have forwarded a very casual mail, but that will suffice or not?
Let me check. Have you sent? Have you kept me in CC?
Yes, ma'am.
Okay. Hmm. I haven't received yet. It might take some time. Hmm. It's not there.
Okay, after this session again, I will do that.
Yeah, yeah, please do that. I haven't yet received. I'll maybe check after 5 minutes again if that would have come. I'm not sure. Are you sure it's not in your outbox? It's sent, right? Just verify that once. Okay, so I think formally we can close the session. So thanks a lot for attending. We can meet next week again, Saturday, 6 p.m. Thank you. I'll be here for till like 8 p.m. So you can still join back and ask questions if you have any. Thank you.
Thank you, ma'am.